Okay, in this opportunity, we are about to start talking about solubility equilibria. And solubility equilibria is pretty much a special case of chemical equilibrium, heterogeneous chemical equilibrium, in which we work with ionic substances and then we express how much of that ionic substance can be dissolved in a certain amount of water. So in this particular case, because it's solubility equilibrium, then we are thinking in terms of a certain limitation from the point of view of, well, you have the ionic substance, and for the most part, you can assume that most of the ionic substances are pretty soluble in water. However, if you remember from back from 170, there are certain situations in which you might produce a insoluble solid, and that insoluble solid is still ionic. At that point, we were just looking at, well, it's insoluble, meaning that you cannot dissolve significant amounts of the solid in water. But that is completely insoluble, it's not quite true, because there is a little amount of that solid that you can dissolve in water. However, because that amount is so little, then we treat that in terms of chemical equilibrium. Okay, and the concept of chemical equilibrium, not because you're working with a solid that is sparingly soluble in water, it means that you're going to do anything different from what you already know about chemical equilibrium. Now, this is again chemical equilibrium, right? And we give the name of KSP to that equilibrium constant. Now, we're referring to this as a heterogeneous chemical equilibrium. What does that mean? Well, forget about this one. This is not what it's supposed to show here. I thought I took care of that. But let's focus on the example here. Okay? Basically, what you have there is a solid, an ionic solid, that you are dissolving in water. And whenever you dissolve any ionic, for that matter, it will separate into the ions. In this particular case, you have lead chloride that will produce lead 2 plus ions right here. And then because you have 2 chlorides there, well, that's what you see there, 2 chloride ions coming out of that reaction. So what this equilibrium is showing you is that that solid is in equilibrium with those ions in solution. The ions are in solution, the solid is, well, a solid is out of the solution. Okay? Any amount of solid or any amount of that substance that is dissolved in water will be present as the ions. Now, if we apply the concept of chemical equilibrium here, these two are dissolved, right? And this is a solid, it's a pure substance. Therefore, it will not be considered in the equilibrium constant. Remember, the equilibrium constant for acid equilibrium, for solubility equilibrium is called KSP. For this particular case, KSP is just the product of the ions. And you follow same guidelines, the law of mass action. You have to raise to the power of the stoichiometric coefficient in that equilibrium. That means you have here our friend chloride with 2 in front of the chloride. So 2 chlorides you have here. So that goes to be an exponent in the concentration. But it's just the product of the ions. So that's why most of the time we don't refer to this KSP as an equilibrium constant. We just refer to it as the solubility product. Because that's exactly what you're seeing there. It's just the product of the concentration of the ions raised to the proper power according to the stoichiometry of that reaction, of that dissolution process. Okay, so let's write that down here. We call this the solubility product. But whether you see it as KSP or equilibrium constant for the solubility equilibrium, it's just the product of the ions. That's why it's the solubility product. Okay? So some common solubility products that you might be working with are here in this table. the analysis here, you may use this pretty much the same as the equilibrium constant for acids. However, you have to be a little more cautious here because the solubility equilibria, it's stoichiometry dependent. What does that mean? So if you compare this to the acid-base equilibrium, the acid-base equilibrium is always one-to-one. No matter what acid you are using, the equilibrium is always one-to-one. So you can compare those solubility, those acidity constants or those basicity constants because the stoichiometry of all those reactions is always the same. So you can look at the constant and you can say, well, a larger constant means it's a stronger acid, right? But here, you don't have that power anymore because you can compare these solubility products directly if the stoichiometry of the reaction is the same. Let's say, for example, if we compare barium fluoride with lead chloride with lead bromide, well, technically all of them are the form mx2, that is going to give you m2 plus 2x minus. Okay? That's pretty much all there is to it. So that dissolution process for each one of those salts is the same. The stoichiometry is exactly the same. Well, for those, you can compare those values of KSP directly. Okay? So, for example, here for lead bromide, that is the smallest one, right? Between those three. So you can perfectly say, well, because this product is smaller, then the solubility of lead bromide is less than for lead chloride or for barium fluoride. Okay, so it's less soluble. Let's write that down. PbBr2 is less soluble than BF2 or PbCl2. Not by much, but yes. So, however, when you try to compare that to PbSO4, for example, or when you want to compare that to MgCO3, then you are losing that power of comparison. You can, because the stoichiometry is not the same, you can no longer say if a larger value of K of the solubility product means that it is more soluble. So you have to be careful here. Okay? So remember, if the stoichiometry is the same, you can make direct comparisons. If the stoichiometry is not the same, then you have to go to a different, you have to do something else to be able to compare. Okay? So more values here. Okay? So these are just the values and they are representing the solubility equilibrium. Remember, here, for example, if we take this, it's representing the equilibrium in which you have a solid, and that solid is in equilibrium with the ions. Okay, iron 2 plus, this is in aqueous form, and carbonate. You are separating into the ions, and therefore KSP in this case is going to be the concentration of iron 2 plus times the concentration of carbonate. Okay. Things to pay attention to is what is the stoichiometry of the reaction. Okay. Now, one of the things that is very, very commonly associated with the solubility product. So we're talking about things that are not that soluble. Some stuff that you want to know what the solubility is in water. And these are very poorly soluble because, well, basically you have the solid in equilibrium with the ions, okay? If it was completely soluble, then all of the solid will dissolve, right? And then you won't have any of the solid. There is no equilibrium. Everything is like a strong acid, so to speak, okay? Everything is separated into ions. Well, in this case, you still have a solid, okay? But we can still refer to the solubility of that solid, and that solubility refers to the maximum amount of the solid that you can dissolve in water. And remember, The solution of an ionic substance implies that all of that substance is separated into ions. Everything that is dissolved in water for that ionic substance will be present as the separated ions. Okay, so keep that in mind. We can apply sort of a regular formula, or I don't find something that is easier to grasp, but if we have this general formula, then the molar solubility is simply a root. What root? Well, it depends on the stoichiometry of the reaction. So it's not a square root, it could be a cubic root, it could be a fourth root. It depends on the stoichiometry of the Ksp divided by the stoichiometric coefficients raised to that power. Okay? Do you have to memorize this equation? I would say, please don't. Don't memorize this. I mean, this is sort of a general idea of what you will be dealing with, but do not memorize that because you're going to get that out of the reaction anyway. So let's see what I mean. So here, molar solubility will be related to Ksp. However, you can compare the molar solubilities directly, but you cannot compare the Ksps directly unless you have the same stoichiometry. Okay? So this is what this is saying. You cannot always compare it directly, just if the stoichiometry is the same. Okay? But the molar solubilities is just telling you how many moles of that particular substance you can dissolve. So in order to compare, if you only have the values of Ksps, in order to compare which ones are more soluble than others, then you have to calculate the molar solubility. And you can perfectly do that if you have the Ksp. Okay? So in this particular case, we have lead chloride, and we want to know what is the molar solubility of lead chloride. So one of the things that we have to calculate this, because we don't have any number in this problem, right? So that means you need Ksp. And Ksp for lead chloride is 117 10 to the negative 5. Okay, so that's Ksp for this particular substance. Now, how do we solve this? Okay, yeah, let me rewrite this equilibrium here. PbCl2, and let's forget about the states for now. So that is the solid, and the solid is in equilibrium with Pb2 plus 2 chlorides. Okay? Now, the way we solve this is that we refer to the solubility of the substance as just as how much of that substance you're dissolving. Okay? And because all of that solid that is dissolved will be present as the ions, then you apply the same stoichiometry, the stoichiometry according to the reaction, to what is the amount, the solubility, the molarity of those ions in solution. Because between lead chloride and lead, the stoichiometry is 1:1, so the amount of lead ions that are dissolved is equal to S. And I'm using S because of solubility, but S is pretty much X when we were doing acid-base equilibrium. Okay? Now for chloride, the story is a little bit different because you will have twice as many chlorides as you have lead ions. Okay? So this is going to be 2 times the solubility. Okay? So let's say if you dissolve 1 mole of lead chloride, you will have 1 mole of lead ions, and you will have 2 moles of chlorides in solution. That's pretty much what we are saying here. But we don't know what the value of S is yet. Okay? So if we have this now, then that means that Ksp is equal to the concentration of lead 2 plus concentration of chloride squared. Now remember, let's use a different color here. This number here is the one you are putting here. Okay? Is the coefficient. If you look at this here, that has absolutely nothing to do with the exponent that you will use on the concentration. It's just whatever is on front of that ion. So be careful with that. So since the concentration of lead is going to be equal to S and the concentration of chloride is going to be equal to 2S, then Ksp is going to be equal to S times 2S squared. Again, I will ask you to be careful with this here. The whole thing is going to be raised to the power of 2. Okay, because that's the total concentration. You are not leaving that 2 out of the exponent there, so be careful with that part. Which means this goes to 4 times, because that's 2 squared, S raised to the power of 3. So you first raise to the power of 2 this S here, times S again, that's X raised to the power of cube of the 3. So that means Ksp equals 4S cubed. If we rearrange this and solve for S, remember we are solving here for S, then S is equal to the cubic root of 1/4 Ksp. And this is going to be equal cubic root of 1/4 times 117 10 to the negative 5. And this is equal to 0.0143. And this is going to be molar. So the solubility, the molar solubility of lead chloride is equal to 0.0143 molar. Okay? Now, what if we do this the other way around? So if you have Ksp, you can calculate the solubility. If you have the solubility, you can calculate Ksp. So in this particular case, you have the solubility, just we don't have the solubility, we don't have the molar solubility, right? So, and this is, normally when you look at solubility tables, normally you don't see a molar solubility, but you see this type of data. So grams per a certain amount of water. So this is a low solubility, of course, but if you're going to calculate Ksp, then you need the molar solubility. So we need to convert these to molar solubility. Okay? And molar solubility is moles per liter. So here we have 100 grams of water. And we have a tiny bit of the solid there. So that solid, that amount of solid compared to the 100 grams is so little that we can perfectly assume that those 100 grams of water would be equal to 100 milliliters of water. Okay? And moreover, if we are calculating molarity, then this is 100 milliliters, right? So we have to convert this to liters, so this is 0.1 liters. Okay? Since we have to calculate molar solubility and these are grams, we have to convert those grams to moles. Okay, these have to go to moles. And for that we need the molar mass of silver phosphate. And the molar mass of silver phosphate is 418,576 grams per mole. Okay? So in this case, well, you need a little more data than the problem is giving, but you have everything that you need actually. Because if you have the formula, you can calculate the molar mass. Okay? So first step is to convert that solubility to molar solubility. So we start with 0.00065 grams of our solid. 1 mole of the solid is 418,576 grams. And since at this point you have moles, the last step involves this dividing by the volume. So this step, the last step here, is doing exactly that. So we are dividing by the volume. So we end up here with 155 10 to the negative 5. Now this number here is S. That is the solubility. That is the molar solubility that we are going to use in the calculation. So our reaction here is going to be silver phosphate. Let's do it formally. The solid in equilibrium with 3 silver ions and 1 phosphate ion. Okay? KSP here is going to be the concentration of silver raised to the power of 3 times the concentration of phosphate. And since we already calculated that the solubility is 155 10 to the negative 5, that is the solubility of the silver phosphate. Okay? Which is going to be pretty much 3 times the solubility of the silver ions and 1 time the solubility of the phosphate. Okay? Therefore, KSP here is going to be the solubility or the concentration of silver ions, which is going to be 3s raised to the power of 3, times the concentration of phosphate, which is simply S. Okay? Now, careful here. 3 raised to the power of 3 is 27. Okay, not 9. So you are not multiplying 3 by 3. Okay, no, it's not 3 by 3, but 3 raised to the power of 3. So that is 27 s raised to the power of 4. Okay, so you have raised to the cube here, plus, but still have one more, so that's s to the raised power of 4. So this is going to be equal to 27 times 155 10 to the negative 5 raised to the power of 4. And this is equal to 156 10 to the negative 18. So this is KSP for silver phosphate. Okay, so if you have KSP, you can calculate molar solubility. If you have solubility, whether the molar solubility or the solubility as given here, you can calculate KSP. So you can go both ways. One particular situation that you may run into is the common ion effect. Now, what does that mean? So if you have something that is a common, for example, in this case, for this equilibrium, okay, you have lead ions and chloride here. If you add something that contains one of those ions, then it will affect the solubility of your ionic substance. So for instance, you are adding sodium chloride. What is the impact of adding sodium chloride into a solution that already contains lead and chloride? So that are in equilibrium with the lead chloride. Well, technically, what you are doing is adding more chloride. And since you are adding more chloride, well, you basically are applying Le Chatelier's principle here. If you are adding more chloride, if you are increasing the concentration of chloride here, then the equilibrium will shift to the left. It means you will dissolve less lead chloride because you already have a certain amount of chloride in the solution. Okay? So, adding a common ion reduces solubility. Okay, now the solubility product will not change. KSP will not change, but the solubility will. Okay, so that equilibrium will respond in such a way to minimize the disturbance. If that means that you are decreasing the solubility, well, so be it. Okay? So how do we use that? So in this particular case, we have calcium fluoride, and then we are adding sodium fluoride to this solution. Okay, we are adding this much concentration of sodium fluoride. So in this case, concentration of fluoride, because the stoichiometry of sodium fluoride is 1:1, is going to be equal to 0.100. Okay, so here calcium fluoride will be in equilibrium with calcium 2 plus fluoride, 2 times fluoride. Okay, this is going to be the solubility of calcium fluoride. So because calcium and calcium fluoride is 1:1, this is S, and for fluoride is going to be 2S. So now, since you have already 0.1 molar of fluoride in solution, this technically has to be 0.1 molar. Okay, and here I'm pretty much using a we can use the full ice table here, but because there is not that much going on, and just everything happens in one side of the reaction, pretty much. So that's why I'm not doing the full ice table, but you can perfectly do so. So the thing here is that Ksp for calcium fluoride is about 146 10 to the negative 10. And you may argue, well, you know what, it looks like the solubility of that calcium fluoride is much less than 0.1. So if that's the case, then you can assume, well, this concentration here is really large compared to the solubility of that ion. So we can probably say, well, this is very small. Okay, pretty much like the X small assumption, it's pretty much the same here. So in this case, then Ksp would be simply S, remember, you know what, let's do it the whole thing. Ksp is concentration of calcium times concentration of fluoride squared. Therefore, Ksp is equal to S times 2S plus 0.1 squared. We are assuming that S is very small. Okay? Therefore, S is going to be equal to Ksp divided by 0.1 squared. Okay? So this is 146 10 to the negative 10 divided by 0.1 squared, and this is equal to 146 10 to the negative 8. So this is the solubility of calcium fluoride in 0.1 molar sodium fluoride. Okay, and let's use a different color here. Okay, solubility of calcium fluoride in 0.1 molar sodium fluoride. Now, how to put it? Perfect question is, well, what was the solubility of calcium fluoride before you added that 0.1 molar of sodium fluoride? Well, we are back here, right? If we forget about this part and we keep our 2s here, then we end up with Ksp being equal to 4s cubed. And therefore, S would be the cubic root of 1/4 Ksp. And if you plug in the numbers, you end up with 332 10 to the negative 4. This value here is larger than 146 10 to the negative 8. And that means that, well, the solubility was significantly reduced by adding that sodium fluoride to the solution, to the initial solution. So you went from 332 10 to the negative 4 to 146 10 to the negative 8. So 4 orders of magnitude reduction. So you reduce the concentration by a factor of 10,000. Okay, so that's kind of the power of the common ion effect. Now there is another situation that is related to the common ion effect, and is the pH. Okay, so in this case, well, there are pretty much, if you remember, there are salts that will have a acid or base character, and therefore if it happens that those salts are also they also have a solubility equilibria, then the pH will affect the solubility of those salts. In what way, so to speak? So if you have a hydroxide, right? Well, a hydroxide, if you increase the pH, means you increase the concentration of hydroxide. If you are increasing this, okay, this hydroxide, what's going to happen? I mean, the equilibrium will shift to the left. You will decrease the solubility of hydroxide if you increase the pH. Conversely, if you decrease the pH by adding acid, basically adding acid is decreasing the concentration of OH minus, and then you improve the solubility. You increase the solubility of that hydroxide. The same thing can be applied to any other salt that will have an acid-base equilibrium. So in this particular case, you have a carbonate. The equilibrium with carbonate is, as shown, two ions of the particular metal plus the carbonate, right? With an acid-base equilibrium for carbonate, well, what's going to happen if you increase the pH? If you decrease the pH, this is not well written. If you decrease the pH, which means you are increasing the concentration of H plus, which is what you have here, then you are increasing this. That means you are moving this equilibrium to the right. So you are eliminating carbonate. And if you are eliminating carbonate, what is you are doing here is you are decreasing the concentration of carbonate. Therefore, in this particular case, if you are decreasing the pH, then this equilibrium will go to the right. Okay, it is a little bit confusing at times, but this is all about Le Chatelier's principle. Okay, how the pH affects the solubility of salts is just about applying Le Chatelier's principle. So, what about we take a look at these ions, shall we? These we are trying to determine whether they are more soluble in acidic solution than neutral solution, right? So we have the first equilibrium is BaF2 that goes to Ba2 plus 2 fluorides. Okay? Now fluoride let's put it this way. In water, fluoride will do this. Okay? So, if we have an acidic media, what is happening? Okay? So, if you increase H plus, right? You decrease OH minus. This equilibrium goes, let me use different colors here. If you increase if you increase H plus, OH minus will decrease, okay? If OH minus will decrease, this equilibrium goes in this direction. That means fluoride concentration will decrease. Now, if you look at the reaction up here, if fluoride concentration decreases, then this equilibrium shifts to the right, and therefore the solubility of barium fluoride will increase. Okay? So it might sound a little complicated, but the more practice you get here, the better. Okay? And that will happen. Those salts will be affected by pH if they have acid-base behavior. Okay? And I'm saying that just because if we take a look at silver iodide, well, silver iodide goes to silver plus and iodide, and neither of one of those have acid-base equilibrium. They don't have acid-base behavior. So this is not affected by pH. The solubility will remain the same regardless of the pH. Now the next one is easier to picture. We have calcium hydroxide goes to calcium 2 plus 2 hydroxides. So what happens if we take H plus and we increase the concentration? Okay, so we're comparing acid versus neutral. So if you increase H plus, then OH minus decreases and this equilibrium shifts to the right, and then here the solubility increases. Okay? Can you you know what, at this point I just want you to be able to predict what happens with the pH, okay, in terms of if you increase the pH, what happens to the solubility, and if you decrease the pH, what happens to the solubility. Can you identify what is going to happen to those salts, to the solubility of those salts if you increase the pH? Okay, that's one thing. The other thing that I want you to remember is what happens if you add a common ion. The solubility will decrease. One thing that I want you to remember here is that, for example, if you have, in this particular case, and I'm sorry that I'm going backwards here, this is common ion effect. You have to add something that shares one of the ions in that equilibrium for you to see an effect on solubility. But if you are adding, for example, if what you were adding was sodium chloride, well, sodium is not participating in that equilibrium, and by equilibrium I mean this one. Neither sodium nor chloride are participating in that equilibrium. Therefore, adding sodium chloride, no matter what concentration you are adding there, will not affect the solubility of calcium fluoride. So that's what is named the common ion effect. It has to provide one ion that is in common with that equilibrium. Okay? Other than that, calculating solubility from KSP or calculating KSP from solubility is the main thing that you need to know how to calculate. Here the pH, we're gonna treat that at the qualitative level, so just to understand what is the effect of pH, higher pH, lower pH on the solubility. Will it increase the solubility? Will it decrease the solubility? That's all I'm gonna ask for, okay? So next step is precipitation, and it's selective precipitation for that matter, but that's a different story.